All right, well, hopefully the video will come out okay. Had some issues with the camera last few days, but it worked fine yesterday, so hopefully it'll be okay today. Last class, we were trying to make a connection between the first derivative, the second derivative, and the shape of the graph. Yes? And what we determined is that the first derivative should give us all the information about where the function is going up and where the function is going down, and that the second derivative will tell us about the concavity of the function, which is the shape, whether or not it's looking like a smile or a frown, right? And what we're going to do today is continue with this, but we're going to add one more thing into this. Not only are we going to find where the function is going up and down, find the local max and mins, find where it's concave up and concave down. Did I use that notation last time, right? Yes. Okay. And find the inflection points. At the very end, we're going to use all this information to do a quick sketch of the function. Now, this is not section 4.4. 4.4 is called curve sketching. And when we get to that section, which will be today, we're going to add more elements into the sketching. All right? So when you get to your homework in 4.3 and it asks you to do a sketch, you're going to do it like I do right here. When you get into 4.4, there's going to be more involved. Got it? All right. Well, I hope that you did attempt the homework. I asked you to look at problems 4, 5, 7, and 8. So who looked at 4, 5, 7, and 8? One? That's it? I want the truth. That's all. Okay, so let me. You did 4.2. All right. Well,
I was just following order. I was like, oh.
The algebra there is kind of messy, right? The problems that you ran into as far as solving equations is not the nice little polynomials we had. And that's what I was trying to stress to you last class. You need to do the homework to be exposed to the types of equations I expect that you can solve. If you're just expecting, hey, I just have to be able to solve a quadratic equation, then you're going to be in for a rude awakening in the middle of a test when you have to solve some sort of trigonometric equation or log equation or something. So please expose yourself to that by doing your homework. And now we move on. I want us to do the same thing we did last class, okay, with the additional step of sketching. And this function is our real first function that is not nice, all right? It's not a polynomial, right? It's not like x to the third minus 5x squared plus 1 or something. This is a weird looking function. These fractional or rational exponents represent roots, right? This is really x, squared, but then take the cube root. And this is really x to the 5th power, then take the cube root. So this is a strange function, and what we're going to do at the end is draw it, see what it looks like. So let's begin. I'm going to need to analyze both the first and second derivatives, so let's go ahead and get those derivatives now. And you know what? I forgot one thing before I do the derivatives. Let's talk about the domain of this function. It has not been an issue in the past. The domain has been nice because everything we've dealt with has been a polynomial, right? This is not a polynomial, so we need to check real quick. The domain of this function, are there any issues? Is there anything you cannot plug in? Do you see any fractions? You don't see any fractions, right? As far as like x is in the denominator, right? So there's no issues with division by 0. But because these are roots, we do have to consider maybe the fact that we could have a negative underneath a square root or a negative under a 4th root, which is no good. But these are cube roots, right? So we're still good. You can take the cube root of a negative number. So the domain of this should still be all real numbers. Y'all fine with that idea? But we need to consider it. So the domain is all real numbers. I put negative infinity to infinity. And that just means all numbers are on the table here. This function we should have a graph. If we graph it, it should go out to the left and to the right forever. And we're going to see what it looks like in the middle. All right, first derivative. I have two terms. I can just do power rule on each of these. So what's the derivative of that first term? 10 thirds x to the
Negative 1/3.
-1/3. Y'all agree? Power rule. Drop the 2/3 down, subtract 1. Next one. So minus
Back to 9. And negative.
10/3 again.
Yes.
X to the 2/3, right? Because we're going to subtract 1 from 5/3, so we get x to the 2/3. Now, we may as well just take derivative again, right, while we're here. So let's do the power rule again. Negative 1/3 comes out, hits that, becomes negative 10/9. X to the
Negative 4/3.
-4/3. And then over here, minus 29ths x to the -1/3. All right, there are the two derivatives that we're going to need. So would you agree with me that these derivatives look a lot different than what we've had in the past, right? And we're going to need to set these equal to 0. So I'm going to take a moment right now to just take a look at these derivatives. And I'm going to start with the first derivative. I just want to kind of play with it a little bit first to see if I can make it look a little nicer.
You're going to set it to 0, right?
I am, but not yet. I'm gonna just make sure I understand what I have here. This is really 10 over 3x to the 1/3 minus 10x to the 2/3 over 3. Is that the same thing? That's this, right? I just take the x to the negative power, drop it down to the bottom. It joins the 3 that was already down there. Now, you might be asking, well, why do that? I mean, do I really need that? And you don't need it, but remember, I am going to be setting this equal to 0. And I know that if I'm dealing with a fractional expression, if I want to set that equal to 0, it's real nice because all I have to do is look at the numerator and say, hey, when is the top equal to 0? But the problem is right now it's not a single fraction, it's two fractions. So I'm going to put them together. How do I put these two together? Common denominator, right? So I need...
Isn't that still a cube root, though, in the bottom of it?
This is a cube root, yes.
Would it be beneficial to go ahead and put that in the cube root or no?
I'll leave it as rational exponents. They're the same. I think it's easier to work with the rational exponents when it comes to, well, you'll see right here. I'm going to multiply the bottom here by x to the 1/3. Don't know why I put that bar there. I'm going to go x to the 1/3 on the bottom and then on the top. See what I'm saying? That'll give me the same denominator. And notice what happens here. X to the 2/3 times x to the 1/3. Add the exponents. 2/3 plus 1/3. 3/3. 1, right? So that's just x to the first power. So this actually simplifies to be 10 here. Take away 10x all over 3x to the 1/3. That's pretty nice. I like the way that looks. If I have to set that equal to 0, it's going to be pretty straightforward, right? If I have to figure out where this is undefined, which I do, right? I have to figure out where this is also undefined. Is it pretty clear to you where this thing is undefined? If x is what? 0, right? Because I get division by 0. So it's, I hope, obvious to you that cleaning it up a little bit makes it a little easier on the eyes, don't you think? All right. So let's go. Let's go ahead and work with this. We'll do the second derivative in a minute. So I'm going to just, I'll just rewrite that over here. First derivative is 10 minus 10x over 3x to the 1/3. And now I'm ready to get my critical numbers. I've made a decision about your next test. The curve sketching is going to be a take-home portion of the test. That's good news for you. I normally don't do that. When it comes to sketching the curves, these problems take like 45 minutes to do. So I could only give you one on the test. So I'm going to give you take-home tests. I'm going to give you 30 of them. No, I'm kidding. No, I just give you like 2 of them, 2 or 3 of them.
You know what? You do have to grade them, so.
That is right. And grading these they're not fun to grade.
You'd be like, oh, well, they grew some lines, they're good.
That's right. They just grafted on Wolfram Alpha. It's all good. All right, so I'm going to set the first derivative equal to 0. Because it's a fraction, I only have to set the top equal to 0. You will have an in-class part of the test, okay? Don't get me wrong here. I'm not saying that the entire test is take-home. The sketching, curve sketching portion of it is going to be take-home.
How many points is that part?
I don't know yet. I need to look at the whole test and see. 20% seems right to me.
So we could all get together as a class, after class.
That will not be allowed.
Nothing cheating.
Yeah, I'll state that on the take-home part that you're not supposed to get help.
So X is 1.
All right, so x is 1 here. Everyone understand I'm just setting the top equal to 0? So x is 1. Now, is this a critical number or not?
Yes.
What do we have to check? There's something I had to check about this critical number before I can say it's a critical number. Is it in the domain of f? And it is, because the domain was all real numbers. So this is good. The other thing I have to look at is where is the derivative, first derivative, not exist, right? And we have not had this really come up, have we? This has really not ever been an issue until this problem. Here, if x is 0, right? Look at the bottom here. If x is 0, 0 to any power is 0. So we're going to get division by 0, aren't we? So we don't want x to be 0. That means x equals 0 makes our first derivative not exist. And that means it's a critical number so long as 0 is in the domain of the original function, which again it is. So we have two critical numbers. All right, now from last class, do you remember what we did with this after we found the critical numbers?
We plugged it back in the function.
Not yet, no, we don't plug in function.
Oh, we did a number line.
Number line. Number line's next. Okay, so I'm going to draw a number line. I'm going to plot the two critical numbers. I always like to put these little critical numbers in boxes so I don't confuse them with the next thing I'm going to get, which are what? Test points. So we find the two critical numbers. Those two critical numbers create a very natural partition of our number line into 3 sections. And we're going to just pick some points in those sections, like -1's a good one. I use a little x there. Circle it. Half, 0.5, and 2. Sounds good to me. And those points are going to be plugged into the original or the derivative. Which one is it? The what? See, do you remember me telling you that at some point this was going to be a little confusing? You have to know what, think about what, now hold on, before you look it up, don't say anything. Think about what you're doing. You're plugging a number into, let's say you plug it into the original function. That's just going to give you the y value of the function, isn't it? If you plug this number into the derivative, then that's going to tell you whether, remember, derivative tells you whether or not you're going up or down, doesn't it? So if you plug this number into the derivative, the sign of that answer, positive or negative, tells you if you're going up or down. And that's what I'm trying to figure out, right? Up or down? So test points always get plugged into the derivatives. All right, test point, -1, go into here. So I'm doing f prime of -1. So plug that in there. What do you get? I think that's 20 on top. And on the bottom, ooh, this is cube root, right? What's the cube root of -1? -1, right? What number times itself 3 times is -1? 1 times 1 times 1. -1 times -1 times -1 is -1. So this is going to be -1, and then times 3, -3. And all I really cared about was the fact that this was what? Negative. That's all I care about, negative. If the derivative is negative, that means the original function is decreasing. So in this little region here, I write f, the original function, is going down. Then we get to plug in 1/2. Let's try and do this one mentally without actually writing it down. Half of 10, 5, 10 minus 5, 5. So I have a positive number on top, don't I? Cube root of 1/2. It's positive, right? That's all I care about. The cube root of 1/2 is positive. Times 3, still positive. So do you agree I'll have a numerator that's positive and a denominator that's positive? Yes. So this will be positive, right? So f prime of 1/2 is positive, and that means the original function is increasing. And then I plug in 2. And I just say to myself, well, look, if it went down and up, then now it's got to go. No, you don't do that. You remember you have to test each one just to make sure. So let's plug in 2. Negative on top. And then if you plug in 2 here, the cube root of 2 is still a positive number times 3 positive, so you should get a negative there. So it does go down, up, down.
But not here.
What's that?
Not here.
Yeah, not in general, we can't say. It's just going to keep switching. All right, now, I think at this point I can answer this first part, right? I can answer this first section right here. Where is it going up? Where is it going down? What are its local max and mins? So let's do that. Let's just do it right here.
Wait, so we know that the critical numbers is where it's 0, correct? Is that why?
The critical numbers are where the function is either 0 or undefined, yes. It turns out for us that it's undefined here and 0 here. But this is also a local minimum. So we're actually going to have a cusp here. It's going to be a cusp if we graph it, because it's a minimum, right? And the only way you can have a minimum is if it does this or something like that, or if it was a sharp V like that. And it's not this because here the derivative is what? At that point would be 0. At these two it's undefined, isn't it? But just because of the nature of my experience with these functions, that does not have a sharp corner. It's not like straight lines. It's not an absolute value function, so it's going to be more like this. That's what's happening here. Here, it's a maximum, right? But the derivative at 1 is 0, so that is going to be something more like that when we graph it. But we'll get to that. Let's not get ahead of ourselves. I'm not saying to you. I answered your question, right? Okay. All right, so let me take that first question here. Where is f increasing? Okay, where is it going up? Just between 0 and 1. And remember, don't grab your test points, grab your actual critical numbers. Between 0 and 1. Do I put brackets or parentheses? Parentheses. Why? Because I told you to just put it in parentheses always.
Because that's always right.
That's always right, yes. That is always right. If you put a bracket, it could be right, but it also could be wrong. If that point's not in your domain, then you can have issues. So we put it in parentheses because we won't get into any trouble that way, all right? Just to be a little more clear on that, if you put this in brackets, for this problem it would be correct because 0 and 1 are in the domain of the original function. So it's okay to include those points. All right, what about down? Everything to the left, so negative infinity all the way to 0, and then union, right? 1 to infinity. How about local max? Local max. Do we have one? At 1, this is where it's happening, right? But we don't know what the y value is. So I'm going to write it like this. It's 1, and then this is a point on my graph. 1, let's plug 1 into the function. See what happens. What's 1 raised to any power? 1. 1 raised to any power? 1. So this really is 5 minus 2? 3. Okay, that's not so bad. How about a local minimum? Do we have one? Yes, that happens here because it goes down then up. And that happens at 0. So I plug in 0, and what comes out of that? 0. So the origin happens to be my local minimum. We good? Questions? Okay. Now, from last class, what I tried to tell you was that if you're going to do the concavity stuff, it's basically the exact same process that we just did, but on the second derivative instead of the first derivative, right? So let's take a look at that second derivative and clean it up first. See if we can clean this up. So my second derivative cleaned up. Let me rewrite it as f double prime of x equals, I'll try and write it as fractions, negative 10 over 9x to the 4/3 minus 20 over 9x to the 1/3. So I just dropped my negative exponents that were on the x, I just dropped those down. They joined up with the 9s that were down there. What is a common denominator? 9x to the 4/3, right? If I could make them both look like that. So how do I make this one look like 9x to the 4/3? Multiply by x to the 3/3, which is just x, isn't it? Right, x to the 3/3, add those together. 1/3 plus 3/3 is 4/3, right? But 3 over 3 is 1, so this is just x. I'm just multiplying top and bottom by x. Understand? All right, so this would become negative 10 here minus what? 20x over my common denominator, 9x to the 4/3. That's not bad looking right there. Again, because I'm keeping in mind that what I want to be able to do to this is set it equal to 0 and figure out where it's undefined, and I think it's going to be easy to work with that.
Can't you just multiply the 9x 4/3?
Can you do what?
You're going to set to 0, right?
I am going to set it to 0 in a moment, yes. There's my second derivative. That's what I'll work with. All right. Where is my second derivative equal to 0? So all I have to do is set the top to 0. What is it, negative half?
No, positive.
I think it's negative half. Let's move things around. Is that number in the domain of our function?
Yes.
Yes, we already knew that. And now I need to see, is the second derivative ever not exist? At 0 again. 0 is in the domain, so we include it. You see, this is like just a duplicate. We're just doing the same thing we just did, but on the second derivative. Now a number line. And make sure I plot these correctly. 0 here, negative 1/2 here. Those are critical numbers, so I box them. This partitions my number line into 3 sections again. And I pick test points. Negative 1, I like that one. 1, I like that one. I guess I have no choice here. Negative 1/4 I could take. And these test points are being plugged into the second derivative, right? We're going to plug it into this to see what happens. What can you tell me, just by looking, what can you tell me about the denominator, no matter what? No matter what I ever plug in. What can you tell me about this right here?
It's going to be either negative or positive.
This right here. Doesn't that mean either x to the 4th and then cube root, or cube root and then x to the 4th, or then to the 4th? Right? That's what this means. What is raising anything to the 4th power going to do? Make it positive, right? So do you agree that no matter what, the bottom is always positive? Always, always? So let's not even worry about the bottom. Let's just look at the top. What happens if I plug negative 1 into this for x? Well, that becomes positive 20, and then take away 10. That's positive, right? So I get a positive here, which means my function is going to be happy, right? Positive, happy person, happy function. How about at negative 1/4? Plug that in here, ignoring the bottom again. If I do 20 times negative 1/4, that's going to be 5 minus plus 5, isn't it? When I put that in here, negative 1/4 in here.
It's minus 5 or plus 5. So
Plus 5, and then together, then now I'll get negative 10. So negative 10 plus 5. Negative 5. So it's negative, and I just looked right into the projector, and I can't see anything but a big bright light right now.
Don't go toward the light. As long as you don't get a headache.
Did y'all hear about that guy that sent out a tweet 2 years ago about the World Series?
Yeah.
Did you hear about that? 2 years ago, he posted that 2016 Cubs versus Indians, Game 7, tied in extra innings, and then what did he say? Something like the world will come to an end or something at that point, or something like that. Anyway, he predicted Game 7, extra innings, those two teams.
You're gonna win.
Interesting.
You have the same
I
thing for,
can't
like,
see.
football and basketball.
What's the chances of
I mean,
that?
dead serious. Like they did that with the Seattle Eagles, Seahawks, and
Man, that light is bright.
This was like a yearbook.
Yeah, I heard about the yearbook also. The guy that on his yearbook at the bottom said 2016 Cubs World Series champions. Yeah, but that was like back in like eight. Yeah, in '93 or something. Yeah. Okay, sorry. Plug in 1 and what do we get? Oh, wait a minute. Yeah, plug in 1. What do we get?
negative 30.
We get negative 30. It's still negative, isn't it?
Yeah.
See? See? You have to check them. Still negative.
Still negative.
It's just the way this behaves.
Isn't that like that bracket thing, like in the NBA, you know, how like they football, like try to predict the bracket?
Oh, we're talking about that now? I don't know what made me think of that. The bright light, apocalypse. I don't know.
Oh yeah, they predicted that with the Patriots, y'all. Seahawks came through.
Okay, let's answer this question, the second part, if we can. Where is the original function concave up?
Between negative infinity to
Negative infinity to negative 1/2. Okay, where is the original function concave down?
negative 1.2.
Careful. Yes, make sure you grab your critical number. Don't grab the test point on accident. That's a lot of people will do that on accident. To infinity. Okay, it's okay that it. Now, well, I have to say this carefully. The reason why I'm going to say negative 1/2 to infinity is because it doesn't switch at 0, right? Right?
0 is not
But
in its domain.
but 0 is in the domain of the function, of the original function. So that means that if I draw this, it's going to stay concave down as I'm drawing it, but since 0 is in the domain, I don't have to pick up my pencil. If 0 was not in the domain, if it wasn't, then I can't say it's concave down here. I'd have to break it into two pieces. Negative 1/2 to 0, union 0 to infinity.
Okay.
Graph, we're about to do it. All right, that's it. Everything I've done is what we did last class, just on a different function. Yes? Oh, inflection points. Sorry, inflection points. Forgot to put that down. What about inflection point? Do we have a change in concavity anywhere? Yes, it is right here at negative 1/2. So I have to take negative 1/2 and plug it into the original function. Now that looks like it might be interesting. So there's the original function. Let me try my best right now to plug that in. I'm thinking about how the book would do this.
Put it in the calculator.
I don't think they're going to do it in the calculator. I just don't think they will. So let's just plug it in. F of negative 1/2 will be 5 times negative 1/2 to the 2/3 minus 2 times negative 1/2 to the 5/3. Right? That's what it would be. I'm curious to see. I took this problem right out of the book. I'm curious to see what they do for the answer. Which number was this? Well, if we need to be able to plot this point in a little while, so we will need the calculator answer. This is number 30. Let's see what they do here. Wait, that doesn't look like it. 32, sorry. heck is it? Can't find it. Oh, there it is. Do you see it? They put 6 over the third root of 4. What? How'd they get that, right? So I guess we should try and get it. All right? So let me kind of take a quick little guess as to how they got this. All right? Here's how I think they got that. I think they looked at the original function to start, and I think they factored out an x to the 2/3. And they rewrote it as 5 minus what? If I pull out 2/3, minus 2x. Because this is x to the first power, and then you would add the exponents, and you would get 5/3. Did y'all see that?
Oh, okay, I see. Because that's 3 over 3.
Yeah. Get used to that idea of what I just did, that 3 over 3 is 1. It happens a lot in this class, from here on out. So if I turn the original function of that, and now I plug in -1/2, let's just see what happens. F of -1/2 would be -1/2 to the 2/3, right? Times 5, then what? -1/2 here?
Yeah.
Which would turn this into +1, which is a 6, right? That's a 6. So I have 6, I'll put the 6 in front, and then I have, let's do it this way, times -1 to the 2/3 over 2 to the 2/3. Is it okay if I do that? Splitting up the fraction into two things. Okay, what's -1 squared? 1 cube root of 1. 1. So I have 6 times 1 over. Now let's do this. What's 2 squared? 4. What's the cube root of 4? I don't know, whatever the cube root of 4 is. And I think that's the answer they had, right?
I think so. 6 over.
It was, yeah, put the 6 on top. Let me bring it back up here. 6 over the cube root of 4.
So you basically just times it by the number on top of it.
Say again?
You basically times it by the number on top and then you
No, you raise it to the number on top and then cube root it, yes. So in other words, we have this. That's the formula that you were using.
So whatever is on bottom, you have.
Is the root. Whatever's on top is the power. All right, we good? Our inflection point was -1/2 and then 6 over the cube root of 4, right? All right, so great, wonderful. How did that happen? Oh. So what's the last step here? Sketch. Now this we did not do last time, right? This is the new stuff. Did I tell y'all that story about when I was in graduate school, the guy who came into the tutoring lab and tried to correct me? Yeah, remember? And he was all mad at me because I didn't do a problem right. He wanted me to apologize. Okay. That same guy, because he didn't like me, he called what I'm about to show you the Bobby method. And the reason he called it the Bobby method is because I told my students I didn't like to be called Bob or Bobby. That my name was Robert, and you can call me Robert, you can call me Rob, but not Bob, not Bobby. So he called this the Bobby method, all right? This is how I sketch functions using calculus. If you want to call it the Bobby method, that's fine, okay? If you remember it, I'm happy. If you remember one thing, it's the Bobby method. So look, the reason why I'm going to show you this is because if you open up a normal calculus book, they do a slightly different approach to this. which I think can be confusing. When I was a student, it was a little confusing to me. So I think what I'm going to show you here is a little more natural. Hopefully you'll agree. You're not going to know the difference because I'm not going to show you the other way, all right? So our goal is to sketch, right? That's our goal. So let's start with a clean sheet of paper, all right? And at the top of the page, give yourself maybe like 2 inches on top. From the top, 2 inches down, I want you to draw a number line. This is not going to be our final graph. All right? Start with that number line, top of your page. And you can try and make it straight. See, mine's not very straight. And on this number line, here's what I'd like for you to put. The critical numbers. The ones you got from the first derivative and the second derivative. So what were the critical numbers from the first derivative? 0 and 1. It was 0 and 1. And what was the critical number from the second derivative? 0 and negative half. So those are the three numbers I'm talking about. I want those three numbers on this axis. Make sure you put them in order, all right? Space them out appropriately. So I'm going to say if this is 0 and this is 1, then this would be negative 1/2. And I'm not going to put any other points on that line. I'm not going to label anything else but those 3 points. With me? All right, from these 3 points, I want you to draw little line segments that go straight up, like this. And I want you to give yourself enough room, like make these tall enough so that you can squeeze into this a total of 3 rows. That means 2 horizontal lines. So do you see I have this number line, and now I have 3 rows, bottom row, middle row, top row. Essentially what I've created is a table, right? You see the table? And this table has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 little sections to it. And I'm going to fill in all 12 sections now with some information. Everything that I put into the first row is going to come from the first derivative. So I'm going to put f prime over here to the side just to remind myself that this information is coming from the first derivative. The second row is going to come from the second derivative. And the top row, you just have to remember, is the function itself. That's the end goal, right? The end goal is to graph the function. So at the very end, up here at the top, we're going to have information about f. Okay, let's talk about this first row, which is the first derivative. When we drew the first derivative, we drew a number line earlier, didn't we? We had 0, we had 1, we had dots, and then we had determined it was up, down? No, down, down, up, down. That's what we had, right? We're going to transfer this information onto that. So look at it. To the left of 0, our function is doing what? Down. So I come over here to 0, and to the left of 0, which is both this box and this box, I'm going down. So I'm going to put a little down arrow here, little down arrow here. Understand? To the left of 0, I'm going down. So I come to 0 here. I'm working in the first row because that's the first derivative, down, down. Okay? Now to the right of 0, until I get to 1, it's up, right? So to the right of 0, until I get to 1, it's up, which I'm going to put a little up arrow right here. And then to the right of 1, it's down. So do you agree with that information? This says that to the left of 0, my function should be going down. Between 0 and 1, my function should be going up. To the right of 1, it should be going down. So that's the same thing, just the only difference is that we're including the second derivative critical number in here also, right? Now let's talk about that second derivative critical number. We did that. We came up with some information. We drew a little table. It looked like this. And it was, what was it? It was happy, frown, frown, like that? Okay, so that's what we had. And I'm going to do the same thing I did here, but now on the second row. So I'm going to go to negative 1/2. To the left of that, I should be what? Positive, up like this, happy. Between negative 1/2 and what? Well, the rest of the way, right? It should be frown, 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 all the way across. Frown, frown, frown. This is not the sketch. No, this is not the sketch. I said this is not, didn't I say at the very beginning?
Yes. Yes.
I did. I said this is not going to be our sketch. Our sketch is coming, but this is not the sketch. This is going to get us to the sketch, though. All right, so let's talk about this. Let's look at this first section, okay? Let's look at F in this first section only for a second. To the left of negative 1/2, right? To the left of it. You've got to be going down, but you also have to look like a smile. So take a look at a smile that we said looks like parabolic. If I asked you to move from left to right, as you start, you would be going which way? Down. And then when you got to the bottom, you would start doing what? Coming up. So on a general smile, you could be going down or up, right? But I can only be going down. So which side of the smile must my function look like? The left side or the right side? It must look like the left side. See, if I'm on the left side, I'm smiling, but I'm also going down. So do you see how I'm going to put this information together with this information to determine that the function itself must look like the left side only? You got it? Now, what about this? You must be going down, but you must look like a frown. So which side of that frown would it have to be? The right side, right? Look at this right here. The only way you can be going down while you're on this is if you're going this direction over here, right? On this side, you're going up. So it's got to be the right side of the frown. Understand that? Understand? Yeah? What about the next piece? You must be going up a frown. Which side? Left side, right? It's the left side of this. And then finally, you must be going down the frown. Right side. Are there any questions on that? Because the Bobby method doesn't work if you don't get that part. You got that? All right. I don't know why you got to be using that your own way of doing it when the book does it different. Use your Bobby method. I can still just, obviously I'm still bitter.
Well, that'd be funny if that turned into a thing and then they actually call it that.
The Bobby method?
Dropped all
That would suck, actually. I would hate that.
It's something.
Okay, so we're ready for our picture, all right? This is it. Now we're ready for the sketch. So what I'm going to do is right below this is why I asked you to do this on a new piece of paper. Right below this is where we're going to place our graph. And I'm going to line things up. So I'm going to start with the number line. This is actually my picture. And I'm going to place these critical numbers right, straight down, okay? So here's 0. I'm going to place 1 here. I'm going to place negative 1/2 here. And then I'm actually going to draw my y-axis in here, right? Because we should have a y-axis and it goes through the origin. So my y-axis goes like this. We good? All right, I know the way the pieces of the function look, right? I just need to like paste them together. And what would be good for us to have right now are some actual points to help guide us, right? And the good news is we already found some points on this graph, didn't we? We found the local max, the local min, and the inflection point. So let's go through those. What was the local max? Where was that? At 1, 3. So I'm going to start jotting these down. I have 1, 3 as a point. I had local min at 0, 0. I remember that one. And then the other one was negative 1/2, and then it was 6 over the cube root of 4, right? And I'm going to break my calculator out. I'm actually going to figure out what that is. So I'm going to take the cube root of 4 on my calculator. Do y'all know how to take a cube root?
on the map, but
if you want to take the cube root of 4, it's the same as raising 4 to the 1/3, right? So you can use 4, then the caret key, and then very important, in parentheses, 1 divided by 3. And that will give you the same. That's the cube root of 4. 1.587? Okay, so take 6 and divide that by that.
3.78.
3.78? Okay. So this point right here is approximately -1/2, 3.78? 78, okay. Approximately. Good enough, right? All right, let's plot these points. Doesn't matter what order we go in. I like 0, 0, and I'll plot, let's use a nice color, okay? Let's use purple. This is going to be my graph. So there's 0, 0, 1, 3. So let's see, let's think about how high up I need to go. I need to go up to 3, but here 3.718, right? So I'm just going to kind of mark out my y-axis. Let's say 1, 2, 3, and let's say this is 4. So 3, I don't know, right about there. You agree with that? And then at -1/2, I'm at 3.78. So up here, that's kind of like ballparking it, right? See it? No questions? Not happy about it? Okay. We ready? All right, let's go. -1/2 here. To the left, it must look like this, right? So from this point, I'm going to draw that shape. And I'm going to put an arrow because I know it continues to do that forever in that direction. Now, from this point to this point, I need to connect them, right? But I have to look like this. So be very careful here. Make sure you don't do anything crazy. See that? That's like a perfect, it was perfect until I came back up there. That's almost a perfect right side of a frown, isn't it? Pretty nice? I don't like what I did there. I really don't like what I did there. There we go. I'm happier with that. Now what about at that point? I've got to get from here to here, and I have to look like this. So make it look like that. What are we going to wind up having there? A cusp. There's our cusp. See it? And then over here, from this point to the right, looks like this. There's our what? There's our local maximum. Yes, and that is our graph.
How's it a local maximum if there's a point higher over there?
Local maximum. Locally the highest point. Remember the difference between local and global. This would be the highest point in this region, yes.
We had to show the volume method in the test.
Yeah, well, unless you want to go teach yourself the method from the book. Are you saying opposed to just putting in your calculator?
No.
Do you have another method?
I could just, from the things that you gave us, I think I could just put it.
What, without this? You think you could?
Maybe.
Go ahead. You can try it. But if it's wrong, I will be less forgiving.
He's lost for
You're supposed to save time.
hint, hint.
You're probably like as you were doing it, you probably like done this while you were solving the inflection points and the local maximums.
Kind of. See, here's the thing. When we did the first derivative, right, and we started drawing the number line and putting the things there, we didn't know what the critical numbers of the second derivative were yet.
No, like writing down arrows and writing up and down.
But see, but you would have other numbers that would show up later that might create new splits in your graph. See what I'm saying? Like if you only did it in the beginning, you would have drawn an arrow here, an arrow here, an arrow here. Later on, the other critical number would come in. That means you'd have to split it into two and draw two. Look, I mean, do what you want. Find your own way. I'm showing you the way that I do. This is it, and take it or leave it. Okay, we're done. That only took 50 minutes. I have done all the other homework problems for this section on the homework solution videos. There are 3 homework solution videos for this section. I did not do number 33, and I did not do number 35. Okay, so I did on the homework video number 4, number 5, number 7, number 8, number 25, 27, 29, 31. I did not do 33 or 35. I did number 33 in my Monday, Wednesday lecture, yesterday's lecture from my Monday, Wednesday class. I did number 33 at the end of their lecture. Okay, it was the last problem we did. And I told them that I'm going to do number 35 in today's lecture. So if you want to see 33, you have to get on my YouTube channel, look up the 2413 Monday, Wednesday class, and go to yesterday's lecture, which is day 19, I believe. And it's the second video, all right, if you want to look at it. And I told them they better watch this one. So you better watch this one, because it's trig. And I haven't done a trig one yet.
Are there going to be a lot of trig ones on the test?
You want a lot of trig ones on the test? Oh, I thought that's what you just said.
Now all we're going to see is
2 cosine theta plus cosine squared theta. Now here's some good news. We only want this on the interval 0 to pi. So when you initially see me write this on the board, you should get all excited because you're like, hey, continuous function, right? Continuous function, closed interval. I can use the closed interval method. Yes, if I'm asking you for the global max and the global min. But that's not what I want. I want you to sketch this. And that means you need this information. All right? So we're going to go through the entire process we just did, except there is a restriction on domain that I'm giving you. And that's to make the problem easier. If we take that restriction off, it's a much more difficult problem. All right, ready? Here we go.
why is it more difficult past that interval?
Well, let's see. We're going to actually see why as we proceed through this, why it would be harder. I'm going to first check domain. I already gave it to us. That's definitely defined in here, right? There's no crazy points in there? All right, so everything's good. Let's take our first derivative. Equals what? Negative 2 sine theta. Yeah, okay, let's take our time. This is chain rule, isn't it? That's cosine squared. So you have something squared, derivative of something squared, 2 pops out, right? 2 cosine theta to the first power, but then times derivative of what's inside, so the derivative of the cosine, which is negative sine. And are we done there?
Yeah.
Yep, that's the derivative of cosine squared theta is this. I'm going to clean it up. Negative 2 sine theta minus 2 sine theta cosine theta. I'll change the order. I don't know why, but it's not wrong to do that, right? All right, there's my first derivative. Now I'll give you the choice. Would you like me to get the second derivative now, or you want me to work with that and come back and do the second derivative later?
Just get it now.
Just get it now? Okay. There's my first. Second. All right, derivative of negative 2 sine theta is negative 2 cosine theta. And then minus, now look, you've got options here. Oh man, does anyone, I wonder, no, okay. It's a double angle identity. You could convert it into a double angle.
Better than the product rule.
Or you can do product rule. But we're not afraid, we're calculus students now. right? So look, -2 is coming for the ride, right? -2 is coming for the ride. I'm going to do a quick product rule because that's not that big of a deal to do a product rule right there. Derivative of sine, cosine theta, times cosine theta, right? Plus, what's derivative of cosine theta? Negative sine theta, times sine theta again. And that would close it off. There's your product rule. That's cosine squared minus sine squared. Would have been nice if it was plus, huh? Because then it would have been the Pythagorean identity. But it's not. It's minus sine squared. So look, -2, this is turning into cosine squared theta minus sine squared theta. No, that's if that was a plus, it would be. Darn it, we got so close. Any questions on that? I'm going to distribute the -2 through, and then I'll be done with my second derivative. All right, there's my second derivative. Well, there's a lot of things we're going to be able to do with that, but I think that's a pretty clean version, don't you? I mean, you could yes, we can mess with some identities, but let's just leave it like that. We good? All right, so I'm going to erase everything else except for our final versions. So our first derivative is right there, and our second derivative is right there, right? And there's our original function. So now we find the critical numbers by setting the first derivative equal to 0. First derivative equal to 0 means I set -2 sine theta minus 2 sine theta cosine theta equal to 0. And this is why you took pre-cal. Remember I said for my pre-cal class, there's two things I want them to know. The unit circle and how to solve trig equations. And this is why. That's a trig equation. I don't like the 2 or that one. I can divide by -2. Let's get rid of them. Both sides. I can do that? Nothing wrong with that. That's algebra. Changes these to positive things, so I like that. Bless you. Any suggestions on how I solve that equation?
You pull a sign out.
Pull a sign out. Factor a sign out. They both have sign, right? So factor a sign out. Sine theta pulls out. We get 1 plus cosine theta is left equals 0. And that's nice. What just happened is really nice. Because I can set each of those factors equal to 0, can't I? So I set sine equal to 0, sine theta equals 0, and then I set 1 plus cosine theta equal to 0, and that's nice. This really turns into cosine theta equals -1. Right, just move the 1 over. And you'll recognize, hopefully, that those are nice values on your unit circle that you should be familiar with. So let me go back. Now this remember you're asking like, why is this important to have the closed interval? If that closed interval wasn't here, then we'd be looking for all solutions to this equation. That's an infinite number of solutions. And same with this. But because we're only looking between 0 and 2 pi, we're going to have a finite number of solutions. So we'll have a finite number of critical numbers. That's a good thing, right? So here's my unit circle. Sine is the y coordinate. That's here and here, right? That's where sine is 0. What are the angles there? 0 and pi and 2 pi, right? Because it's part of this, right? 0 pi and 2 pi. So that's what I'm getting here. If theta is equal to 0 or pi,